Hi and welcome back to another LeetCode video. Today we're going through the bit manipulation problems on LeetCode.io. And the next problem we're going to tackle is the reverse bits problem. And it's an easy problem, LeetCode 190. The task is to reverse the bits of a given 32-bit signed integer. So the number of bits in the integer is fixed, it's 32 bits. And we're giving this number as a decimal value, as a number in Python, and we need to basically compute its binary representation, and then from that representation, reverse all the bits and then compute the decimal representation of that number once we've reversed the bits. Now what is good is that the number is going to be larger or equal than 0, which is good for us, so we don't have to deal with signage with signed or negative values. And what we will need for this is, well, we need to understand how do we actually get the binary representation of a number, and then how do we compute the number from a binary representation. Those are the two directions that we need to go to. So let's have a look. If we have a number, let's say 5, and base 10, how do we compute the binary representation of that number? Well, the algorithm is very simple, and it's something you should probably memorize or know after doing a couple of these bit manipulation problems. What you do is you have a loop that runs for as long as n is larger than 0, right? This is going to be the loop. And inside the loop, what you do is you compute the bit, and that is equal to n modulus 2. So the rest of the integer division of n by 2. And then you update the value of n by performing an integer division with 2. And this keeps looping until n reaches 0. So now, if we take the example of 5, what will happen is, well, we get 5. 5 modulo 2 is going to be 1. Then we update 5 by dividing it by 2. And 5 divided by 2 as an integer division is 2. Now we perform the same operation with the modulo. 2 modulo 2 is 0. Now divide 2 by 2, which is 1. Now we perform another modulo, and we divide 1 by 2, which yields 0, which means we're going to break out of the loop, right? So that's the end. And now we've pulled out the bits 1, 0, 1. Now what is important is, because we had the whole number in the beginning, n5, and we performed the modulo 2, we know that the first bit we pulled out is the least significant bit. So it belongs at the end of the binary representation. It belongs here. And this 0 belongs here. And the other one belongs in the first position. This order is really important. Unfortunately, because I chose 5, it looks as it's the same forwards and backwards. Okay. Now, how do we convert a number back into decimal representation? And maybe we should take I wonder if we should continue with this example. Maybe we should just expand this and not make this 5. If we say we started at, I'm just making this up now. So let's say this was 10 in the beginning. Then the first modulo gave us a 0. Right. Right. So the binary representation of 10 in base 10 is 1, 0, 1, 0 base 2. Right. So how do we convert 1, 0, 1, 0 to a decimal number? Now, this is also quite simple, but you have to wrap your head around this. Basically, what you do is you take, well, you take a number, you multiply it by 2, and you add the digits. So in the beginning we have 0, right? So this will be kind of our seed. You multiply it by 2, and you add your digit 0, right? So now what you do next is you take this expression, multiply it by 2, and you add your next bit, right? And this continues until you've iterated over all of these numbers. So this will be plus 0 here. And finally, we have a plus 1 here. So this will be the 0. And I should have written plus 1 with plus 1. So this is how you compute the decimal number. And if you compute this, so this will be 0, right? This will be 1 because 2 times 0 is 1. 0 plus 1 is 1. Now you multiply it by 2. So that becomes 2 now. Sorry. Plus 1 times 2. Oh yeah, we need another times 2 in the end here, I believe. Not mistaken, yeah. 0. This will be 1. This will be 2. And then we're going to add times 2 plus 1. So we'll end up with 5. And then times 2 again, and then we'll end up with 10. Right? So that's how we compute that number back. Now, if you write it like this, you can do the same thing that we did here. You can put that into a loop where you just have a loop, and every time in the loop you're updating your result as result times 2 plus bit, right? And you iterate over all of the bits that you have. So this is actually the reverse thing that we're doing up here. I don't know if you can see that, but it's exactly the reverse operation. And actually, this approach requires us to start with the least significant bit as well. Whereas here, this approach gives us the least significant bit. So we can combine these two methods to compute the reverse order of a number in a single loop. And that's what we're going to do. So here, well, what we'll do is we'll initialize a result variable. And we're going to return that at the end. And now in our range, because we know it's a 32-bit signed integer, and in the examples we can see that actually all 32 bits are listed. It's not enough to just, convert the number to a binary representation and then stop, because the rest is going to be 0, which, if n is 0, that means we would stop. So we'd actually stop at this point. So we have to modify this loop a little bit. And, well, we have to make sure that we iterate exactly over 32 potential bits, even if the last ones are all 0. So we just do this instead of while n is larger than 0. Cool. So now we're going to pull out the bit. That's n modulo 2. Then we're going to update n, right? And now we just need to update our result. And result, well, that's exactly what I said it is. It's result times 2 plus the bit. And so this is now, well, because it's 32-bit, it's constant time. But if you imagine that we had an unlimited number of bits, then it would be linear in however many bits we can have. So let's run this, see if we have any errors that we didn't see. No, so that works nicely. And we can submit this. And okay, that completes another LeetCode problem. So the trick to this one is really to ensure that you iterate over all potential 32 bits. Because if you do this while n larger 0, you're going to get the wrong results. And the second insight is to realize that getting the bits out of a number, or getting the bits from a number returns them in order of least significance, and building a number from bits places the most significant bit first, which is why this multiplication here works. Right, so this concludes this problem, and next we're going to attack the missing number problem.